So in this talk, I'd like to talk about the symmetry spans that first I'm going to explain, and that enforces gaplessness. So, and this talk is based on the ongoing work with Takamasa Ando, who is a student at the Yukawa Institute of Theoretical Physics in Kyoto University. Okay. So the theme of this talk is to diagnose the gapless modes in the physical system. So main question is that say you have some microscopic description of your physical system, and what is the macroscopic property of the system? So does that look like a conductor or insulator, for example, and vice versa. And the question in the other direction is that if you want to have some material that has a magical property, and then so if you dream of it, then you want to know what can be the microscopics to design maybe some magical materials. So both directions are interesting questions. And in this talk, among those possible properties, in this talk, I'm focusing on the gaplessness or gapness. That means that so the system is called gapless when there is an excitation whose energy can be infinitesimally small in the thermodynamic limit. And the example of that is a conductor that you only need very small amount of energy to transmit signal through the copper wire. On the other hand, of course, the tires is an insulator, and you cannot do that. Okay. And so and the symmetry is a very nice tool to do this to answer to this kind of questions. So let's say that, so this is a schematic diagram. Let's say that we start from the UV theory, the microscopic theory, and then we do the RG flow. So that's a coarse graining procedure, just zooming out, and then you have a TIR, which is the macroscopic effective description. And let's say that we have some symmetry, microscopic symmetry acting on microscopic theory. And then, the fundamental fact about symmetry is that it also acts on the microscopic symmetry, also acts on the macroscopic symmetry via some map from the microscopic symmetry to macroscopic symmetry induced by this RG flow. So that's the basic fact. So we can use this kind of scheme to say to constrain the possible IR physics. So if you know this part, then you in particular know that this thing acts on this thing, and that constrains what this TIR can be. Or if you want to cook up TUV that realizes the particular TIR you have in your mind, and then one thing is to find a nice symmetry and realize it in the microscopic model. So that so that's the main theme of the talk. And and one particular very well known and strong example is the two-fifth anomaly matching. So in the case that the symmetry is just a conventional group symmetry with a two-fifth anomaly, and in particular that this symmetry, the group is a continuous, and this anomaly is a perturbative anomaly, then the two-fifth argued that this alone shows that the TIR has to be gapless. So there has to be massless excitation. And so the question in this talk is that can we find other situation where we can say the gaplessness and based on the UV symmetry structure. Okay. And so this is upshot. So instead of thinking about a single symmetry, we think about the two symmetries acting on your system, and then assume that these two symmetries shares one subsymmetry. Okay, and And in this situation, that the of course, it depends on the choice of the symmetries, but it happens that sometimes you can rule out any topological field theory compatible with this symmetry response structure. So that's the upshot. And so when we can exclude the TQFT compatible with the symmetry structure, then the possible IR phase is either gapless or maybe some more exotic gapped but non-TQFT phase. But I just call it the gapless phase. Okay. And
so if you start with the lattice, the gap has to close. How fast is the closing?
So here my argument is by excluding the non-TQFT. So I at the moment I don't have any comment on the rate of the closeness. Thanks for the comment. And it can certainly be the non-relativistic CFT, for example. That's
easier than it's not a CFT.
Yeah. But still gapless. Yeah.
Can I ask?
Yes.
What's the difference between assuming you have a symmetry span and just asking that the push out acts as a symmetry?
So that's the same, and I will comment on that. Yes. So then and this condition is as I will present that directly applicable to lattice system. So the continuous symmetry with the fifth anomaly is either impossible or extremely hard to realize on lattice, and instead this structure itself can be directly realized on lattice system and use it to argue the gaplessness of the system. Okay, and the example suggests that the condition I'm going to present has a close relationship to the fifth anomaly or perturbative anomaly, but that's going to be a very non-trivial thing to show. Okay, so that's the upshot. So then this is the plan of the talk. So I first recall some backgrounds, and then I will explain the main criteria and go through the examples. Okay, so here I'd like to not only just the group symmetries, I just want to talk about the general symmetry, and in this theme of this collaboration, that this general symmetry is defined as all topological operators in your system, and of course you can also try to relax this topologicalness to the more weaker notion. But let me in this talk I assume full topologicalness, and then this topologicalness immediately tells you that the algebra invariance. So because you can just the operator is topological, so you can just inflate to your macroscopic scale. Okay, so that's this map, and mathematically for the finite symmetry, it's described by fusion category or higher analog of that. And in particular for the invertible just group symmetry, it's the categorical avatar of that is the category of vector bundles on the group, finite group, or a higher version of it. And also this categorical gadget can incorporate the information of anomaly classified by the invertible theory, one dimension higher. These are space dimension here. Okay, and the continuous case, we've heard a lot of talks yesterday, and also Matthew's talk in the pre-meeting, and also other papers. And so here I just, for the sake of this talk, I just write this bold vect, but it should mean some category shifts, but I don't need any detail of that. And I also like to talk about the lattice, and that's a categorical gadget. As far as I know, it's not very established. But yeah, I direct point one important paper that studies the detail of this structure in the particular case of Kramer's one-year symmetry. Okay. So, okay, and so we'd like to exclude the gapped phases based on some symmetry structure. So we need to think about the gapped phases, possible symmetric gapped phases compatible with the symmetry. So if you have just a single symmetry, then this is just notation that I'd like to use the TQFT of S means the category of, or higher category of TQFTs with an S action. And then so if you have your microscopic symmetry acted by SUV, and if this theory is in a gapped phase described by TQFT, then this IR fixed point is an object in this category. And so mathematically, this TQFT, when I write a TQFT of S, then that just means that the category or higher category of modules of this whatever category describing the symmetry, and which should be free realizable for this to be a nice TQFT. Okay, and okay, so this gadget, whatever it is, gives you the classification of possible gapped phases, and this is very convenient to in this talk. Okay. Yes.
If there are some symmetric gap phase, and maybe there's some regularization realized as some kind of fractal phases, would you count this as low energy theory satisfy your symmetry TQFT or not quite?
Okay, so this TQFT is a very nice. Okay, so the fractal phase doesn't count as a TQFT, and so that's is in the in this non-exotic in my terminology, that's the exotic non-TQFT gapped phase. Yeah, so that can be possible So I'm not going to exclude that possibility.
No problem. Thank you.
Yep. Okay, so for example, there's just a finite symmetry in 1 plus 1D, and with maybe anomaly, and then just so we want to know the classification of modules of the H-graded vector space, category of H-graded vector spaces, and the standard result about the fusion category is that the module is in one-to-one correspondent to the way of gauging of this H symmetry. So the way of gauging is just the choice of subgroup of your ambient finite group, and also the choice of trivialization of the anomaly. And so that classifies the modules or TQFTs, IR phases, and the physics of it is that this choice describes spontaneous symmetry breaking of H into K, so K is preserved symmetry, and then stacked with the K SPT alpha. So you have vacuum for each element in the coset. Okay. I have two remarks here. One is that you can also think about the direct sum of different TQFTs, and that corresponds to some degeneracy, vacuum degeneracy coming from not because of H, but maybe something else. And also, like so here in this 1 plus 1D, the IR phases are described by the pair of SSB and SPT, but it's not the case in the higher dimensions. And yeah, but in this talk I mainly focus on the 1 plus 1D case. Yes.
In your terminology by TQFT, are you including the possibility of having topological local operators or not?
So yeah, I allow.
Okay, thanks.
Yeah. So that's the direct sum. Yes. Okay, so further specialized to just the Z2 case, then it's just there are two possibilities. One is just a SSB. The Z2 is spontaneously broken, or not. So there are just two things. So the two category of Z2 symmetric TQFT is just generated by these two over n integers. So just the general object in this category is direct sum of this phase and that phase. Okay, so these n1 and n2 are non-zero integers, non-negative integers, sorry, and each of them describes some accidental degeneracy coming not from Z2, so something else. Okay, and okay, so let's do the same thing for the non-invertible symmetry. So Tambara-Yamagami. So the Tambara-Yamagami fusion category is contains the three simple objects: identity and eta, which is Z2, generate Z2, and D describes the Karamazov duality. And fusion rule is this. And yeah, so strictly speaking, there are two versions of it in the difference of the F symbol, but it doesn't matter in this talk. And okay, so there's only one simple module for this Tambara-Yamagami Z2 category, which is itself, and so that describes a full SSV phase. So there are three vacua corresponding to each of the simple objects. And the action is exactly the same as the fusion rule. Okay, and so that just a TQFT, this symmetric TQFT, the category of symmetric TQFT is of course generated by this thing. So so general object is just a direct sum of this Ty. Okay. Okay. And then in the later part of this talk, it's going to be important to restricting the symmetry into subsymmetry. So in this case, we can, so as an example, we can talk about the Tambara-Yamagami Z2 and its subsymmetry, which is just a Z2 generated by eta. And then, so if we have this functor, tensor functor, then we can also the pullback functor between the two categories of symmetric TQFTs, and just the physical meaning is just a restriction of the symmetry action. Okay, so in particular in this case, so this TQFT TYZ2 has only one simple object, which is TYZ2 itself, and it has three vacua, and the eta action, the Z2 action of the vacua is summarized by this. So you see that this pair of vacua breaks the Z2, while this D preserves the Z2. So the image of the pullback, of this T/Z2 is the direct sum of the SSP phase and the symmetric phase. So this corresponds to this pair, and this corresponds to this thing. Okay. And so you can understand this by noticing that the Karamazov duality D that exists on top of the Z2 symmetry exchanges this phase and that phase. So that's the how Karamazov duality works. Okay, so as mathematical equations, if you think about the image of whole of the category of TY-Z2 symmetric TQFTs, then that's generated by this particular direct sum over n. So general element object of this category looks like this, and that's a proper subcategory of TQFT-Z2. Okay, so a general element object of this thing can have a different exponent here, but the image of this Prurbach puncta is just have to have the same exponent. So that's a proper subcategory, and that's going to be important. And lastly, I'd like to talk about a continuous symmetry. So in the case of continuous symmetry, situation is different because once this element in the connected component of D group is spontaneously broken, then Nambu-Goldstone theorem tells us that there's a gapless mode, which we call Nambu-Goldstone mode. And the mental picture is always the Mexican hat potential. So this potential breaks the U1 symmetry. So this black dot is a vacuum, and then you can of course naturally see the flat direction in or going around. So that's the gapless mode. And so in 1+1, actually further the Marmin-Wagner theorem tells that even in relativistic system, this spontaneous symmetry breaking doesn't occur. But anyway, there is no gapped phase coming from the spontaneous symmetry breaking of the connected element. So the G TQFT for the connected G is just SPTs, or generated by SPTs under direct sum. And so the one way of restate the fifth argument for the gaplessness is that if this G further has an anomaly, the anomaly excludes the possibility of SPT, so then there's no possible TQFT. So that's one way of rephrasing the old argument. And so then the idea is to impose another structure other than structure other than anomaly that also can prohibit this particular SPTs. Then we can exclude the TQFT TQFT phase. Okay, so that has been the background. And if there is no question, or yeah.
The case of anomaly is more like a general, in the sense like, are you giving one necessary imply the other, or is there some? It's like if and only if statement here, or it's just one direction? What do you try to say here? I'm not getting.
Here, just this direction. Yeah, I mean, yeah. Here, just if you assume that the anomaly, then there is no compatible TQFT, but yeah, and I'd like to say that in a sense that the opposite direction is not true. That there can be some other structure that can also exclude the TQFT possibility, but that's not within the exact logic. Yeah. But anyway. Which one? So the second one is because of this SSB is not allowed. If you want the TQFT. IO. And the first one is that generally this SPT is non-anomalous. Okay, so in higher dimensions, yeah, you need a bit more to but yes. So this argument is more straightforward in 1+1D. So everything this is anomaly in 1+1D and anomaly in SPT. Oh yeah, so this SPT is a SPT in that dimension, not in the higher dimension. Okay, yeah, yes. Yeah, so I'm going to present a condition which is a general applies to general dimensions. Yes. Okay. So the main criteria is this. So as I said, I assume this orange structure. So we assume the two symmetries, C and D, and sharing E. Okay, and of course if you have this structure, then this structure should be further embedded to the larger symmetry, generated by C and D, but it's not a direct product in general. And we can also, as Jake pointed out, we can also think about the push out, the universal one fits universal symmetry that fits in the square, but that is big. So even if for example, if you think about just the finite symmetries, the universal one is going to be like free product, and only relation is coming from E. So that's an infinite group, and that is a type of group that we do not see as a symmetry of any system. So that's very big, and we can say that that big symmetry acts on the system, but that's in a very non-faithful way. So the faithful thing that acts on the actual system is going to be way smaller than the universal thing, and of course non-universal. Okay, so it's better to focus on, for that reason, that this orange region and make the statement only based on the orange region, which is going to be universal statement. Okay, and so assuming this structure, and then okay, so we can consider that corresponding TQFT category of TQFTs, and so we get the pullback factor from each. So this is the square, and so assume that your IR theory is gapped, described by TQFT. Then you should have a object in this category, so this corner, and then you can just restrict your symmetry action into the subsymmetries. But of course, this square commutes. So in particular, if there's such TQFT, then you have a pair of TQFT, the C symmetric TQFT and D symmetric TQFT, which matches when you restrict to E. So that's this equation within the TQFT E, or in other words, that for this thing exists, this TQFT exists, then the image of the pullback of IC and ID should be non-zero. Okay, so if it's zero, then there is no consistent TQFT. Yeah. Yes.
Or an element in epsilon when I go to two different tracks to have to agree in S phase, or do you even care?
So these squares all commutes. So,
They all commute.
Yeah.
Okay, yeah. Thank you.
Yeah. So if you can find the situation that this image doesn't intersect, then we can conclude that there is no consistent TQFT that can describe your IR. Okay. So the example I know that I did either of one of them should be continuous, but I don't have any no-go theorem about the
Because, at least naively, I think that whenever you only have finite symmetries, then you can never exclude spontaneous breaking.
Yeah, but I'm not exactly sure that if you have two finite symmetries and sharing some subsymmetry, then it typically generates the universal one is infinite symmetry. So then it might generate some non-finite thing, and that might exclude the any TQFT. But I do not have any such examples yet, at least. Okay. And so in this talk, I almost focus on this setup. So in so first I focus on the 1 plus 1D, and I assume that one of them is a continuous symmetry. And of course, I assume that the anomaly for this continuous symmetry is 0. Otherwise, it's already gapless, a lot of to fifth. And the other one might be like invertible or non-invertible. Okay, so that's the setup. And so let me talk about the example. So the example of the symmetry span that excludes the symmetric TQFT is this. So I pick just U1 and also Tambara Yamagami Z2, and I declare that these two share Z2. Yeah. And so as I said, the image of pullback of the TQFT TYZ2 is this. So generated by the Z2 broken phase plus Z2 symmetric phase, and maybe further accidental degeneracy, because the Kramer-Sawanier symmetry exchanges two phases. On the other hand, for U1, so U1 cannot be spontaneously broken. Okay, so the pullback of this thing is just generated by vect. So this is a symmetric phase. In other words, U1 cannot be broken in TQFT, and therefore, like if you focus on Z2, then Z2 is also not broken. Okay, so and these two are not compatible. There's no intersection, so it's just 0, and there's no symmetric TQFT at all. So the universal one is big. This is just a universal. So just saying this structure without saying the actual system, then we can only talk about the universal one. And the universal one is very big. Just the object consists of the word from the alternating from the object from here and there. So it's very big thing. I'm going to. Oh, okay. Yes.
I guess that the universal one is not the minimal. It's both, right?
That's a kind of maximal one,
right?
Yeah.
But is there a sensible concept of the minimal symmetry that contains both?
I mean, there wouldn't be no unique or universal minimal one. There are multiple choices.
I see.
Yeah. Yeah. So the example of system admits this structure is just a compact boson with a particular radius, and so here the U1 is a shift symmetry, just shifting your compact boson, and then at this particular radius, there's a Tambara-Yamagami symmetry so gauging the Kramer-Sawanier symmetry is by gauging this Z2 subgroup of shift symmetry and taking the T dual. So that's, and then okay. So from the argument I gave you, we know that this system is gapless. Of course, because this is free theory, so you of course don't need the fancy argument. But anyway, and what happens in this example is that winding symmetry. So there's another U1 symmetry in this compact boson, and with a mixed anomaly with a shift symmetry, and that is generated by these two symmetries. So if you sandwich your symmetry operator for the shift symmetry with this chromos 1 duality, then you get the sum of winding symmetries. And so in this way, these two symmetry generates the winding symmetry, which have mixed anomaly with the shift symmetry. So, so this is the so the full symmetry is kind of like mix, slight the kind of union of the U1 squared and the chromos 1 duality. Okay, so that's what happens in this case, and we can also consider the lattice version of compact boson, which is XX chain. Yes.
Can you hear me?
Yes. Yes.
Good. So can you summarize just physical statement, maybe for Subir and me? Sorry. For the example, you know, there's two slides. You try to say if I have a U1 global symmetry and T temporal Yamagami Z2 and with Z2 symmetry, and do you want to have some condition on the anomaly to rule out 1 plus 1D symmetry TQFT?
So if you see this structure, you don't need this. Sorry. This structure. So just temporal Yamagami and the U1 symmetry, and then Z2 is shared. Then you can conclude that there's no TQFT. There's no gapped phase described by nice TQFT.
But is there also an anomaly statement for that these symmetries?
So it's kind of, I'd like to interpret it as kind of anomaly, but I don't have any precise thing. And in the example, in this particular example, it has clear relationship to this mixed anomaly with the U1.
Yeah, I see.
Yeah. But I don't have any proof that this is always the case.
So in some sense, you are using just even global symmetry structure to constrain the IR phase.
Yeah.
Even not necessarily the full anomaly concept. In some sense. Yeah. Thank you.
In this example, I guess you're saying there happens not to be a relevant deformation that respects the symmetries?
Yeah.
I suppose there could have been, and in that case, you would say that if you deform by this relevant deformation, then it would have to flow to a CX.
Sorry. Yeah. Okay. That's so in this. Okay. This is too strong. Yeah. In this particular example, this is true, but in general, you're right. But what you can say is that the IR has to be gapless. Yes. Actually, no, I guess no. Yeah, so far. Yeah. Okay. So let me go to the lattice. I'll go into lattice, and the lattice. So we consider just a spin chain, and then there's the lattice version of temporal Yamagami acting on this spin chain. And basically, this chromos 1A exchanges the X Pauli operator acting on J's side of the spin chain sends to the product of Z's and vice versa. And then and I don't have a nice mathematical theory of this kind of structure because the D squared actually D squared is a lattice translation, so it's not actually the fusion category is emphasized in this paper. But anyway, what I need to argue the gaplessness is just this, and this just holds because again this chromos 1 symmetry on lattice is again just Z2 gauging, so the same. I can conclude that this image of pullback should be this. And I further impose the U1 symmetry, whose charge is just the sum over X. And then there's a nice Hamiltonian that commutes both with this U1 symmetry and D, which is this. This is just an XX chain written in a bit weird basis. And it's known that the XX chain is in the IR, flows to the compact boson at the special radius that I talked about. And what happens on lattice is that pointed out in this paper and also further studied in the Shuhen and others paper, is that if you impose the Kramers-Vanier and this U1 symmetry, then of course these two generates another U1 symmetry generated by this thing, and it's known. It's originally found by Onsager that these two operators generates an interesting infinite-dimensional Lie algebra, which now called Onsager algebra, and the XX chain Hamiltonian written in this basis commutes with both of them. So, and therefore entire Onsager algebra. And also like it's studied in the Shuhen's paper that these two U1 symmetries exactly flows to the two symmetries in the IR compact boson description. Okay, so on lattice that this XX chain symmetry has its own algebra that's generated by non-anomalous U1 and Tamara-Yamagami. Okay, so and yeah, here I'd like to slightly emphasize that so from our argument that these two, the gaplessness on lattice and the on continuum is endured by the almost the same structure of this symmetry span. Okay. And there's a ZN version of this story. So you can consider the ZN finite Heisenberg algebra acting on each side. So now each side has a Q dit. And then still, we can think about the Tamara-Yamagami. In this case, Tamara-Yamagami of Zn exchanges x and z daga z. And then, so if we assume this charge, the U1 charge, then these two generates another U1 charge. And it's known that these two also generates the Onsager algebra, so isomorphic to Onsager algebra. And I didn't write the Hamiltonian explicitly, but this paper found a symmetric interacting Hamiltonian commutes with 3. Okay. And it flows to depends on the sign of the Hamiltonian. It flows to either the c equals to 1 or c equals to 3 times n minus 1 over n plus 1. So studied in the integrability literature. And the c equals 1 case, I believe, should flows to the compact boson with the particular radius, the square root of n times the self-dual radius. Yeah, I have no idea. I'm not sure about what is the actual CFT in the other case. Yes.
Yes, slide, but could you say again why, or maybe even one slide earlier, going back to this Kramers-Vanier example, can you say again why the theoretical framework that you're talking about is still applicable even though you don't have an exact fusion category symmetry on the lattice?
Okay, so here I'm, okay, yeah. It's basically that if you assume that there is a Z2 symmetric vacuum, then that means that on lattice you can you can have a unitary that makes it just the tensor product state. Then we do this Kramers-Vanier action that's just Z2 gauging. And then we get the Z2 broken vacuum. So in that way, that actually at least the physicist way that we can show that there has to be a direct sum of two phases. Oh yeah. In this case, yeah, I don't have any comment about this phase. Yeah, I'm not sure that the pitch point in the modular space of safety. Yeah. Of course, it should admit this symmetry. So yeah, some special point. Yes.
Assuming the Witten model SU2 level n-1?
Sorry.
The other CFT, is it the Western Witten SU2 level n-1?
So the same central charge,
Yeah.
but I
Emergent
believe
algebra?
it should be the exact deformation of that.
I see.
It's a marginal deformation.
Because the symmetry is less.
Yeah, symmetry is less. Yeah.
Yamagami as Zn.
Yeah, there's a mismatch between N and SU to level K, actually. So, yeah. Yeah, I agree. Yeah, it's more like that the U1 part, the other U1 part is this radius. Yeah. Okay. Okay, so so far this part has been non-invertible. It doesn't have to be, and it can be invertible symmetry with anomaly. Okay, so this example I picked just a Z2 cubed symmetry with type 3 anomaly, such that if you pull back to the Z2 squared, say the first two factors, and the anomaly trivializes. So there's such anomaly. And then, so in this situation that the image of pullback is generated by direct sum of SPT with the trivial SPT and non-trivial SPT for the Z2 squared. And also there's a, it can also, you can also spontaneously block this one of the Z2s. But anyway, so generated by these two possibilities. On the other hand, image of pullback from a TQFT U1 squared. So I embedded Z2 squared into the U1 squared. And then U1 squared has a deformation class of SPTs. U1 squared SPTs is point. So if you pull back, then it's just one SPT. And yeah, actually this particular image depends on the choice of tensor functor. But anyway, it's generated by the single SPT, and therefore there's no overlap, intersection between the two. So there's no TQFT. And yeah, so the actual system admits this kind of structure is, for example, we can take the spin for level 1 W model, and on that, or this is of course the same as the Dirac two copies of Dirac fermions, they bosonized with a shared fermion parity, and in the lattice system you can also realize on lattice. Yes.
In this example, what is the total phase generated by Z2 cube and U1 square?
So
what's the lower right corner?
Oh yeah. So in this case, it's just the spin 4 times spin 4.
I see. So they generate the entire spin.
Yeah.
So 4 times spin 4. I see.
It's kind of weird, right? We only in this case, it's not the entire spin 4. It's u1 squared times u1 squared. Sorry. But yeah, so this we are just naively assuming that u1 squared and one more z2, but because of this anomaly, that it has to generate the entire copies of u1 4, and that's kind of weird. And yeah, so finally, I just to emphasize that this thing can apply to higher dimensions, just briefly present the higher dimension example. This is just an uplift of a compact boson example to 3+1D Maxwell. Then, so yeah, so you just assume this is just a one-form symmetry, the scary way of writing one-form symmetry, Z to one-form symmetry, and it has a higher analog of Tamura Yamagami for this Z to one-form symmetry. And we also assume that Z2 is enhanced, embedded in the U1. And then, yeah. Now again, like there's a higher form version of Navier-Gosson theorem advocated by this paper, the original paper, that if this bound form U1 is spontaneously broken, then there's going to be gapless photon. So so there's no TQFT in particular, and we can argue that there's no TQFT compatible with this structure. And what happens, and this structure is realized in the Maxwell theory, this particular coupling. And what happens in this case is also like this structure generates the another one-form symmetry, which is magnetic one-form symmetry, and it's known that magnetic and electric one-form symmetry has a mixed anomaly. So that's exactly the uplift of compact boson example. So the pattern in examples that I know so far is that if you work on the continuum, then this faithful symmetry contains a continuous symmetry, which is way larger than we originally imposed, and that with anomaly. And on lattice, that it generates Onsager like infinite dimensional algebra, and then also like under RG flow, this Onsager infinite dimensional Onsager algebra collapses to the continuous group. Yes. Okay, so it's just my laziness, but I haven't studied the lattice version of the Maxwell. Yeah. Okay. So yeah, the big question here is this always the case? This is just an observed pattern in the examples, and I don't have any general argument that this is always the case. Okay, so just a summary slide. So in this talk, I proposed a criteria for gaplessness based on the two symmetries sharing bound subsymmetry. And yeah, so the first question is what I've said, and also like most of the examples on lattice is free so far, but this ZN clock model is interacting. So I hope that there is more interacting lattice examples for this kind of systems. And also like I only briefly thought about the higher dimensional examples, and it would be very interesting to seek such. So I finish my talk here. So.